I have 1 month, so the theta is associated with 3 months, 0.693. Minus sign in front, don't forget. The gamma 1 is minus 0.669. Well, I can round that to 0.7. The minus signs cancel. And what I end up with is 0.99 or something similar. Depends on your rounding. Okay, easy. How many points? Maybe 2 points for the knowing the formula and another point for the correct calculation? No, 1 point only. Okay, it's a short question. Second B, you're supposed to test whether the coefficients of the lagged differences are significantly different from 0. Both of them. So, test for omission of variables. The null hypothesis is the parameters are 0 for one variable and another one variable. So there are 2 of them. Test statistic f being given. Determine the Wald statistic, the value, when testing for the omission of the variables. Can you reject this null hypothesis at a 10% level? And of course, as always, why? Well, how many restrictions? 2. So, the exam is not quite correct. You cannot exactly determine the Wald statistic. You can only approximate the Wald statistic because it's R times F. The general result, general relation. So what we get approximately, that's good enough of course, is 1.375. Compared with a chi-square distribution with 2 degrees of freedom. On the front page, you have quantiles of the chi-square distribution with 2 degrees of freedom. 10% level, so you need the 90% quantile, which is equal to 4.6. The quantile much larger than this value, so the answer is no. I do not reject at 10% level, but that's given already in the problem. Since Wald, I don't have to repeat the value necessarily, is less than chi-squared 2 degrees of freedom with 0.9. And of course, to make sure that you don't make a mistake, you can say, well, yeah, this is 0.4605, and maybe 2. Three more points to gain. First one. A. Consider the regression of log real money demand. We never looked at the data on log real GDP. Well, it doesn't matter, just 2 variables. Log M is regressed on log Y. There's a coefficient, and values which are not of interest I deleted, but except for that, it's the Gretel output with an R squared and with a Durbin-Watson statistic. Step 1, run the static co-integrating regression. Step 2, use the residuals, the U-hats as Gretel calls them, and carry out an augmented Dickey-Fuller test. That's how Engle-Granger test for co-integration works. It provides a test statistic, and it provides an asymptotic p-value, and problem A refers actually to step 2. You can see it on the screen altogether now. What do you conclude with respect to co-integration of log M and log Y? How would you formulate an answer? Now, seriously. (11a). You have to know those things. Step 1, I'm running a static regression. Step 2, I take the residuals and test them for a unit root. That's what the Dickey-Fuller test does. Actually, Gretel is telling you this in step 2. Take the residuals and test them for a unit root. And then you get a test result. T-statistic, large p-value, larger than 10%, larger than 20%. The only thing you have to know is what is the formulation of the null hypothesis. And it works as follows. Well, the short answer is, and then I give you maybe the reason why, we talk about 11a. What do you conclude? No co-integration at conventional level. That's another way to formulate it. For example, 10%, 5%, 1%. Since the p-value, which is given as 23, is larger than, for example, 10%. So I'm not quite sure why you not gave me the answer to the problem. Do you not know how to interpret p-values? I think you know that. So it's rather about the null hypothesis, which you were not sure about. Okay. We only learned it yesterday, so you did not have much time to learn this. For that reason, that would be the correct answer, and let's look why this is the correct answer. What did we learn yesterday about the, maybe you look at the manual, because that's what you have at your hands. We are in the section where we have static regressions. We run one variable on the other variable, and the idea is to perform with the residuals an ADF test. And what happens? The residuals under the null hypothesis of no co-integration meaning, in the notation that we have here, if we have a linear combination between y and x, any such linear combination will be I1. Because co-integration means there's a stable relation. I have a linear combination which is stationary. No co-integration means any combination of y, t, minus some constant, minus some b, x, t is integrated of order 1. That's no co-integration. That's what we learned actually explicitly in the first section. But I know it's only been yesterday. So here's the definition. Cointegration if there exists a linear combination which is stationary, I0 to be more precise. If no such vector exists, then they are not cointegrated. Well, since y and x themselves are integrated, if no co-integrating relation exists, this means any linear combination is integrated of order 1 as well. That means the empirical residuals. Can you still read this? This means the residuals, well, let's call them U hat, like in Gretel. Last day of teaching, you see, we're running out of pens. All the work we did. This means the U hat, as Gretel calls it, will be I1. Because U hat is a linear combination of the data. Yeah, U hat is, of course, nothing else but whatever you call this, A hat minus B hat xt, and there's a y missing. So what you do is you have, if you compute residuals, you have your data minus, you estimate something else. It's a linear combination of the data, and if any linear combination is integrated of order 1, this means the residuals are integrated of order 1. This is the null hypothesis of no cointegration. So again, the situation is often we have a substantial formulation of economic interest of a null hypothesis, and that it has to be rephrased or reparameterized in terms of something which we can estimate, which we can confront with the data. So yes, null hypothesis in words, no cointegration, becomes any linear combination of the series is I1. Hence, I cannot check infinitely many linear combinations. So to make this operational, I say, well, then I compute residuals. They are one specific combination, and they are integrated of order 1 under the null hypothesis. All this is equivalent or an implication. And how do I test whether a univariate series is integrated of order 1? Apply a unit roots test, an ADF, or unit root test to U hat. This is step 2. Right? That's how Gretel works in this, for this test. Step 1, the potential cointegrating regression, the static regression. One variable, log m or y or whatever you call it, is regressed on one other variable, x or log y. Save the residuals. Step 2, execute an ADF test on those residuals. And all that Gretel does is not really interesting. How many legs, for answering the problem, of course, only. How many legs were included, blah, blah, blah. The only thing you have to look at, what is the p-value? It's large. Larger than 10%, larger than 5%, larger than 20%, larger than any conventional level. So the p-value tells you reject the null hypothesis, and then you just have to know what the null hypothesis is. That's why the answer is no cointegration at any conventional level, since the p-value is larger, since p-value is large, larger than, say, 10% or whatever. Okay? Well, B is even harder to, because it's not just looking at a p-value. B is even more on the understanding side. (11b). With respect to step 1, so coming back to the static co-integrating regression, which we have as a result, how can you explain the values of the coefficient of determination, the R squared, and the Durbin-Watson statistic? Well, we begin with the Durbin-Watson statistic. What we have learned in our manual is going to static regressions, and the first proposition tells you if you have y and x, which are I1, and they are not co-integrated, then I expect the Durbin-Watson to be small in the sense close to 0. So, going back to our exam problem, first step, co-integrating regression, the Durbin-Watson was, well, it's not 0, but it's a long way from 2. It's kind of close to 0. So a formulation that I proposed to myself, what was it? What's at the end of the page? It's kind of difficult to read. Durbin-Watson close to 0 is caused by absence of co-integration of I1 errors. So again, what is the precise question? The precise question is, with respect, not repsect, but respect, sorry for that, with repsect to step 1, how can you explain the value of the Durbin-Watson statistic? Under no co-integration, errors being integrated of order 1, Durbin-Watson is close to 0. This explains the value 0.2. And why is there a hint to the graph? Both series display linear time trends. As we can see from the graph. Approximately, more or less linear time trends. Even if they're not co-integrated, a regression removes the trends. We get residuals without trends. Because we can always, if there is a linear time trend in two series, I argued yesterday, we can always reformulate one of the series in terms of the other. Let's look what the manual tells us with respect to that. This is in section 9.3. Section 9.3 is on simple regressions, just 1x with linear time trends. That's our situation. And at the end of section 9.3, we read the following. If there's no co-integration and you have linear time trends, then proposition 9.2 does not apply, but it is still true that we can always rephrase one variable in terms of the other variable, only that the deviations are no longer integrated of order 0, but integrated of order 1. It doesn't tell you that this is true in the manual, so I'm telling you now. Well, it's only the mock exam, it's not the real exam, so this question is a little bit hard. As I said, it's about understanding. If the situation is as follows, let's copy what we have on the manual. Yt is called, it's C plus dt plus I1. I don't give it a name. Similarly, xt is given as a plus bt plus I1. So both of them are what we called yesterday integrated with drift. I1 integrated with drift. Then I can rephrase Yt. Is this still readable from your angle? As alpha plus beta xt, but the remaining stochastic term is a linear combination of those two I1 terms plus I1. So I can always, since x has a linear trend and y has a linear trend, I can rewrite y in terms of x, namely in terms of the linear trend. However, the remainder term will be, of course, I1. So if you do a least squares regression, least squares minimizes residual variance. It estimates this beta actually consistently so that we can get something which is of a smaller variance. I'd like to explain more on this because, look, if you have a I1 situation, a trend situation, what does the R squared do? R squared is defined as kind of empirical variance of the fitted values divided by the variance that we observe. If we have a linear time trend, the sample variance, the sum of squared demeaned variables, is getting massive because what you do when you compute your R squared, you estimate a sample mean, and obviously the deviations from the sample mean get very, very, very large. So clearly what you get is Yt minus y bar is really large. But there exists a linear combination, I just told you, between y and x that cancels the linear trend. So remember, the R squared can also be rewritten as 1 minus sum over the squared residuals divided by the same Yt minus y. That's another way to write the R squared. Now, I'm not writing once more, but I'm reminding you, of course, least squares tries to get the variance, which is so massive in y due to the linear trend, because I'm not accounting for the linear trend when computing the sample variance. Least squares does what the name suggests. It tries to make this variance as small as possible. So it picks as a linear combination the beta such that the linear trend and the x linear trend are removed. They are no longer contained in the residuals. Hence, even if the residuals are not stationary, they will be no longer have a linear time trend. So the epsilon t, or yeah, let's call them now epsilon because they're called epsilon t in the R squared, will not have a linear trend. We can check this with Gretel, but it's kind of clear. One trend, another trend. Take a linear combination that removes the linear trend. That's what least squares does. And this means, of course, that in our plot, went the wrong way. Careful. The residuals are of quite a different nature. They vary around 0. They don't have a linear time trend. So this is my epsilon t, and they behave like, still non-stationary. But something like this. And the deviations of those residuals from the 0 line are clearly much smaller than I'm repeating the deviations of y in blue from the straight line. No, not from the straight line, from the horizontal line. So there's a y bar, and clearly the deviations of y grow and grow and grow much more strongly than the deviations of the error term from the 0 line. So that is the reason why this guy is of a much smaller order than that guy. This is the reason why the R squared is close to 1, even if there's no co-integration. I did not explain yesterday in the lecture, so I explain now. Yes, that's the reason why whenever you have time series with linear trends, you regress them on each other, R squared will be large, mechanically. Linear time trend, massive variance, no more linear time trend, not so large the variance. Whether it's a nonsense regression, whether it's a co-integration regression, whether there's no co-integration, the R squared in the presence of a linear time trend will always be close to 9. 95 minimum, 97, 99. So don't be proud, yeah, I've explained 99% of my data. All you did is you regress one variable with a trend and another variable with a trend. Doesn't explain much, not necessarily. Okay, I have not forgotten about the break, but that would have been the wrong point to stop. So today we finish early because we are invited to lunch and we should be at the bus stop at 11:45, meaning we should stop here at 11:30, meaning we have now 10 minutes break, and then we talk about maybe some other issues. We talk about topics which are not relevant for the exam. I've prepared a file for you. So yeah, I'm suggesting come back in 10 minutes.
Đang lúc đó